All right, 7th graders, let the fun begin. We are now going to graph cube root functions. So what are you going to learn? You're going to graph cube root functions. You're going to compare cube root functions using average rate of change. And you're then going to solve real-life problems of cube root functions. So let's start with our idea. Now, what does a parent function look like? What does a cube root function look like? Well, here we go. A cube root function, just take a look at it, looks like this. Ooh, ah, isn't that nice? So read it to yourself as I read it to you. It says a cube root function is a radical function with an index of 3. Now you're like, whoa, what's that mean? That means it's a cube root. It's an index of 3. That's all it means. The parent function for the family of cube root functions is f of x equals the cube root of x. And here's what it looks like. There's no maximum or minimum. It just like swings like this. The easiest way is, like, notice there's just 3 points. They plug in 1, you get 1. The cube root of 0 is 0. The cube root of -1 is -1. If you wanted to go further and do the cube root of 8, that's going to give you 2. 8, 2. -8, -2. The domain and range are all real numbers. And why is that? Because you can take the cube root of a negative. So therefore negatives work here. The graph increases on the entire domain. Notice, increasing, 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 still increasing, 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 still increasing. It increases the entire time. You can transform graphs of cube root functions in the same way you have transformed graphs of other functions. Example 1. Here it is. Now, what do you think is going to happen? Just look at it. -4. -4 just means the whole graph is going to go down 4. So, I don't know if I have it on here. I'm going to see. Looking for structure. Here we go. Use x values so that the cube root of a radicand is an integer. Don't make this harder on yourself. You can get decimals. That's fine. But personally, I want to make this as easy as possible. So x and h of x. So let me think. What is a number I can take the cube root of? Well, I can take the cube root of 8, or -8. -1, 0, 1, and 8. The cube root of -8 is -2, -4 is -6. If I fill out the rest of this table, this is pretty easy. It's just basic math. We plug it into our equation, we get those 3 values. Your domain and range are both all real numbers. Actually, I should do x equals all real numbers and y equals all real numbers. And I just graph it. -8, -6. -1, -5. 0, -4. 1, -3. 8, -2, which I ran out of room for. And it would look something like that. Now, if you needed to compare it, which you do, what would you say? You would just say the graph of h is the translation 4 units down from the graph of f. Example number 2. Graph this and then compare it. Well, if you graph and compare, just look at it. What do you think's happening? Well, you know that it's going to go left to, and it's going to be reflected. So I'm just going to plug in values of x and g of x. Notice I don't use y because that's not y. So what can I plug in? Well, I want to make this -8. So if I want to make this -8, well, I'm going to plug in -10. That gives me the cubed root of -8, which is -2, multiplied by negative, which is +2. Now I want to get -1 underneath the radical. So -1, That means I want to do negative 3. If I plug that in, cube root of negative 1 is negative 1 multiplied by negative would be positive 1. And if I want 0 on the inside, I'm going to plug in negative 2. That gives me 0. Then I'm going to plug in negative 1. That gives me positive 1. Cube root of 1 is 1. Multiplied by negative is negative 1. And lastly, we plug in 6 because that gives me 8 and the cube root of 8 is 2. So I get negative 2. If I graphed all of these, now negative 10, 2, let's see, negative 7, negative 8, negative 9, negative 10. It'd be like something like right here. Whoops. I can actually graph 6, negative 2. And there we go. There's your graph. If you compared it, what would you say? You would say that the graph of G is a translation 2 units left and a reflection in the x-axis of the graph of F. And there's your answer right here. The graph of G is a translation 2 units left and a reflection in the x-axis of the graph of F. In the next one, let 2 multiplied by the cube root of x minus 3 plus 4. Let that be g of h, or g of x. Describe the transformations. Well, what do we know? Well, we know it's translated where? 3 units to the right. We know it's translated 4 units up and it's stretched by a factor of 4. So if I make a t-table, I'm just going to tell you the t-table. Once again, you can get decimals, you can plug in anything you want. But if I plugged in negative 5, 2, 3, 4, and 11, that once again would give me the cube root of negative 8, negative 1, 0, 1, and 8. So then I get all nice, neat numbers. This would be 2, 4. Nope, that's not right. And let's try that again. If you plug in negative 5, you get 0. Negative 8, yep. And then you plug in 2, you get 2. That's negative 1, negative 2, yep. 3 gives you 4. 4 gives you 6. And 11 gives you 8. If we graph these, negative 5, 0, 2, 2, 3, 4, 4, 6, 7, 8, 9, 10, 11, 11, 8. Obviously, your graph paper, you'd make this work. It looks something like that. And once again, your domain and range would both be all real numbers. So comparing average rates of change. The graph of a cube root function is shown. So as you can see, the graph is right there. Compare the average rate of change of m, this is the graph of m, to the average rate of change of the cube root of 1/4 x over the interval 0 to 8. So let's do our m. So let's see, if we plug in 0, that's going to be 0, 0. If we plug in 8, that's going to be 8, 8. Well, that's easy. Change in y, change in x gives us 1. Piece of cake. Our h function. If we plug in 0, that gives us 0. Just basic math here. If I plug in 8, well, 1/4 of 8 is 2. And the cube root of 2 is what I'd have for my y value. So the change in y would be the cube root of 2 divided by the change in x, which is 8, which is approximately 1600ths. So we want to compare the average rate of change. Well, the average rate of change of M, we want to compare them. Now, there's no verbiage here. There's no meaning to any of this. So what can you tell me? You could say the average rate of change of M is 1 and the average is H. But, what does that mean? You could say this. The average rate of change, remember, this is your comparison statement. The average rate of change of M, well, if you divided, you obviously see that this one's bigger. So you can take 1 divided it and see that M is approximately 6.3 times greater than the average rate of change of H. That would be your comparison. And lastly, solving real-life problems. The shoulder H in centimeters of a male Asian elephant can be modeled by this. I know, you're probably thinking, really? I can actually just take the shoulders of something and have it modeled after a cube root function? T is the age in years, that's time. Use a graphing calculator to graph the function. So let me put the graph up here while I'm still talking. Estimate the age of the elephant whose shoulder height is 200 centimeters. So there's my function. Well, the shoulder height, remember, is H, that's height. So we want to know when I plug in 200 there, when would it be? Well, we just look at our graph. Here it is. What did I use to graph this? I graphed 200. And then I graphed the function given to us. And then I just intersected it. You didn't have to graph this. You could have easily... Now, okay, let me back it up a little bit. That would mean I'd plug in 200 for H. And I get this. Remember, when you graph, you can take this and set it equal to y, and take this and set it equal to y, and graph both of them, find the point of intersection. You could have also just graphed this and just moved your cursor and saw when your y value is over 200. So as you can see, estimate the age of an elephant. Well, the average age of an elephant is between 7 and 8 years old. That'd be fine. Or you can say about 8 years old.